Niels Bohr, born in 1885, stands as one of the most influential scientists in the history of physics. At a time when the structure of the atom was mysterious and puzzling, Bohr introduced a bold new idea that changed everything. He proposed that electrons do not move randomly inside an atom. Instead, they travel in specific energy levels, and they can jump between these levels by absorbing or releasing energy. This simple but revolutionary concept became known as the Bohr model, and it provided the first clear explanation of why atoms produce unique light patterns, known as spectral lines. When we talk about the history of science, there are certain moments that stand out as turning points moments when humanity took a leap forward in understanding the universe. One of these moments happened in 1913, when a young Danish physicist named Niels Bohr introduced a new idea about the atom. This idea would later become the Bohr model, one of the most important scientific concepts ever created. It reshaped physics, chemistry, and even modern technology. To understand why this model became so revolutionary, we need to explore the scientific world before Bohr, the problems he tried to solve, the brilliant solutions he proposed, and the massive impact his model had on science and society. Before Bohr entered the picture, scientists already knew that atoms were made of smaller particles. The discovery of the electron by J. Thomson in 1897 had begun to reveal that atoms were not indivisible, as earlier scientists believed. Thomson suggested a plum pudding model, where electrons floated inside a positive sphere, like raisins in a pudding. But soon, this model was challenged. In 1911, Ernest Rutherford performed his famous gold foil experiment and discovered the atomic nucleus. His results showed that atoms are mostly empty space, with a tiny, dense, positively charged center surrounded by electrons. This led to a planetary model of the atom, electrons orbiting the nucleus like planets orbiting the sun. Although Rutherford's model looked elegant, it had a major flaw. According to classical physics, electrons moving in circular orbits should constantly lose energy. As they spiral inward, they would soon crash into the nucleus, but this didn't match reality. Atoms are stable, they do not collapse. So how could electrons stay in place without losing energy? This question became one of the biggest problems in physics. The old models could not explain why atoms were stable, or why they emitted light in specific patterns called spectral lines. Something deeper was missing. Enter Niels Bohr, a brilliant thinker with a fresh perspective. Bohr realized that classical physics could not fully explain the behavior of tiny particles like electrons. He believed that atoms operated under different rules that were new, strange, and yet more accurate. He borrowed a concept from Max Planck's quantum theory. Energy is not continuous, but comes in tiny packets called quanta. Bohr boldly decided to build a new atomic model based on this idea. Bohr proposed that electrons travel in distinct orbits around the nucleus, and each orbit corresponds to a specific energy level. But the revolutionary part was his suggestion that electrons were allowed only in certain orbits, no in-between paths. This idea was completely different from anything classical physics suggested. According to Bohr, an electron could move from one energy level to another only by absorbing or releasing a specific amount of energy. This change in energy happened in quantum jumps, which were instantaneous transitions between levels. This simple concept solved the biggest mystery: why atoms do not collapse. Bohr argued that electrons in allowed orbits do not radiate energy. They stay stable as long as they remain in these fixed paths. This was a bold and imaginative idea because it went against centuries of classical thought. Yet it worked beautifully. Not only did this explanation describe a stable atom, but it also clarified why atoms emit light in specific lines. When electrons jump to lower energy levels, they release energy in the form of light. Each jump corresponds to a different color or wavelength. This was exactly what scientists observed in experiments. The hydrogen atom became the first great test of Bohr's model. Hydrogen, the simplest element, has one proton and one electron. Before Bohr, the spectral lines of hydrogen were known but not fully understood. They formed a mathematical pattern, but scientists did not know the reason behind it. Bohr applied his model to hydrogen and produced formulas that matched the observed spectral lines perfectly. This was a breakthrough. It proved that the model wasn't just an idea. It could accurately describe reality. Bohr's model changed the way scientists thought about atoms. It introduced the idea that nature works in discrete steps rather than smooth, continuous flows. This was the beginning of quantum mechanics, the field of physics that would later revolutionize the world. Although the Bohr model had limitations and would eventually be replaced by more advanced theories, it still provided the essential stepping stone. It was the first to combine classical physics with quantum ideas, showing how these two worlds could work together. One of the most impressive features of the Bohr model is that it provided a visual way to understand atomic behavior. Students and scientists could imagine electrons moving around the nucleus in fixed orbits, each orbit representing a different energy level. This mental picture made the model easy to teach and understand, and it remains widely used today for educational purposes, even though we now know the real picture is more complex. In reality, electrons behave more like clouds of probability rather than tiny planets, but Bohr's model laid the foundation for the modern understanding. Another important aspect of the Bohr model was its boldness. At a time when most scientists were not ready to abandon classical ideas, Bohr dared to introduce something entirely new. He believed in the power of quantum thinking even before it was fully developed. His willingness to challenge traditional theories showed bravery and creativity. It is this courage that makes Bohr such a remarkable figure in science. He trusted his ideas and followed them despite criticism and confusion from others. Bohr's work did not stop after creating his model. He continued to refine and improve atomic theory and became a leading figure in the development of quantum mechanics. Yet, the Bohr model remains his most iconic contribution. It was a turning point not only for physics, but also for chemistry. Chemical behavior, bonding, and element properties depend on electron arrangements. Bohr's model provided the structure needed to understand the periodic table, chemical reactions, valency, and the stability of elements. Suddenly, ideas that seemed mysterious became logical and predictable. The Bohr model also influenced the rise of modern technology. Without a clear understanding of atoms and electrons, inventions like lasers, nuclear energy, transistors, and modern electronics would not exist. Bohr helped provide the theoretical background that allowed engineers and scientists to manipulate atoms and energy in useful ways. Even though Bohr did not foresee all these applications, his model was the first step toward them. But perhaps the greatest impact of the Bohr model was philosophical. It changed how humanity understands reality. Before Bohr, the universe was thought to operate like a clock, predictable, continuous, and smooth. Bohr introduced the idea that at the smallest scales, the universe behaves in ways that seem strange and discrete. This idea challenged human intuition and forced scientists to rethink their assumptions. It opened the door to quantum uncertainty, probability, and complementarity, the concepts that now form the heart of quantum physics. The development of the Bohr model also reflects Bohr's personal qualities: patience, curiosity, open-mindedness, and respect for scientific discussion. He worked closely with other great scientists, including Rutherford, Planck, and Einstein. His collaboration with them made his ideas stronger and more refined. The story of the Bohr model is not just a story of one man's idea, but a story of the scientific community working together in the early 20th century to understand the mysteries of nature. Ultimately, the Bohr model stands as one of the most important milestones in science. Even though more advanced quantum theories have replaced it, the model remains an iconic symbol of the scientific revolution that changed everything. It represents the moment when classical physics gave way to quantum physics, and when humanity took a deeper step into understanding the atom. Bohr's courage to think differently allowed science to move forward into the modern world. His contribution does not fade with time. Each generation of students begins their journey into atomic physics by learning the Bohr model. It remains the starting point for understanding the behavior of atoms, light, and energy. Bohr's model is more than just a diagram. It is a piece of scientific history that continues to shape the present. The story of the Bohr model becomes even more fascinating when we look at how Bohr tested his ideas, defended them, improved them, and used them to push science into a completely new era. His model was not just a scientific guess. It was the result of deep reasoning, bold imagination, and careful comparison with experimental data. While the classical physicists of the time held firmly to old ideas, Bohr introduced a radical new way of thinking, one that accepted the strange, discrete nature of energy. To continue understanding why his model was so revolutionary, we need to explore the deeper scientific, historical, and conceptual consequences of his work. After publishing his 1913 papers on atomic structure, Bohr quickly became one of the most discussed physicists of his generation. His model was surprising, almost shocking, because it didn't follow the traditional laws of motion. According to classical physics, if electrons were orbiting the nucleus, they should radiate energy continuously, slow down, and fall inward. But Bohr declared that electrons in special orbits do not radiate energy at all. They simply stay where they are unless they jump to a different orbit. This idea was unlike anything scientists had proposed before. It introduced a broken version of classical physics, broken on purpose, because nature itself broke the rules at the atomic level. But Bohr didn't stop at proposing quantum orbits. He also introduced the idea of quantum numbers. These numbers described the allowed energy levels of electrons. Each orbit had its own specific energy, and the electron could only occupy orbits with certain quantum numbers. This solved many long-standing puzzles in physics, because it explained why atoms emitted specific wavelengths of light. When electrons move from a higher quantum level to a lower one, they release a photon whose energy matches the difference between the two levels. That energy difference corresponds exactly to certain wavelengths, producing the spectral lines observed in experiments. This explanation was powerful because it connected theory to experiment. It showed that light is not just a wave, but is tied directly to the behavior of electrons in atoms. This was one of the earliest confirmations that quantum theory was essential, not optional. Classical ideas could no longer fully explain nature. Another important part of Bohr's work was how he explained atomic stability. The nucleus is positively charged, and electrons are negatively charged. According to classical physics, these opposite charges attract each other, and electrons should spiral inward. But this never happens in real atoms. Bohr pointed out that electrons in allowed orbits have a fixed energy that keeps them from collapsing into the nucleus. The concept of stable orbits was one of the key contributions of the Bohr model. Without it, atomic behavior would remain a mystery. Bohr also improved the understanding of atomic size. His formulas correctly predicted the radius of the hydrogen atom, called the Bohr radius. This was an impressive achievement because it showed that atomic structure could be calculated mathematically. The Bohr radius became one of the most famous numbers in physics, and it is still used in modern quantum theory. His mathematics helped scientists understand how electrons behave at the smallest scales, something that was impossible before. The success of the Bohr model with hydrogen was undeniable, but scientists wanted to know if it worked with other elements too. This is where things became more complicated. Hydrogen has only one electron, making it simple to analyze. But heavier elements have many electrons interacting with each other, which classical physics could not explain easily. Bohr tried to extend his model to multi-electron atoms. He made progress by introducing the idea of electron shells, where electrons group together in layers around the nucleus. This idea eventually became essential for understanding the periodic table. Bohr's shell model helped explain why elements have repeating chemical properties. It showed that the arrangement of electrons around the nucleus defines how atoms react with each other. This was a major breakthrough for chemistry. Much of modern chemical theory is based on electron shells, even though the exact details have been refined by later quantum mechanics. As Bohr continued developing his ideas, he also began influencing scientific thinking in a broader sense. He realized that atomic behavior could not be understood with simple pictures alone. He introduced the principle of complementarity, the idea that particles like electrons can behave both as particles and as waves, depending on how they are observed. This principle became a foundation of quantum mechanics, showing that nature cannot be described in only one way. Instead, different perspectives reveal different truths about the same object. Complementarity was a philosophical breakthrough as much as a scientific one. It showed that the limits of observation are part of the laws of physics. It also opened debates about the nature of reality itself. Bohr's discussions with Einstein became legendary. Einstein famously disliked the uncertainty of quantum mechanics. He believed the universe should follow strict, predictable laws. Bohr disagreed. He thought uncertainty was a natural part of the quantum world. Their debates shaped the evolution of quantum theory and remain some of the most important conversations in scientific history. Even as new quantum theories emerged in the 1920s, Bohr's original model remained important. Werner Heisenberg, Erwin Schrödinger, and others built more advanced mathematical models of the atom using wave mechanics and matrix mechanics. These new theories provided more accurate predictions, especially for multi-electron atoms. But Bohr's ideas were still at the heart of the new theories. His concepts of energy levels, quantum jumps, and discrete orbits inspired the wave functions and probability clouds used in modern quantum mechanics. The Bohr model eventually became a simplified representation, useful for teaching basic concepts, but not fully accurate for describing complex atoms. Yet it remains important because it represents the first successful attempt to merge classical and quantum ideas. Without the Bohr model, the development of quantum mechanics would have been slower and more complicated. It was the spark that ignited a scientific revolution. Bohr's contributions went beyond theoretical physics. His work played a major role in shaping modern technology. Understanding atomic behavior helped scientists develop lasers, atomic clocks, semiconductor devices, and many other technologies that define the modern world. The Bohr model helped create the basic understanding needed to manipulate atoms and electrons in practical ways. Even though Bohr did not design these technologies himself, his ideas were the foundation for them. Another interesting part of Bohr's story is how he influenced young scientists. Bohr founded the Institute of Theoretical Physics in Copenhagen, which became one of the most famous scientific centers in the world. Many of the greatest physicists of the 20th century studied or worked there. Bohr encouraged open discussion, debate, and collaboration. His leadership style nurtured creativity and helped shape the culture of modern science. Some of the most important developments in quantum mechanics came from researchers who were inspired by Bohr or worked closely with him. Bohr also believed strongly in ethical responsibility. As nuclear research advanced, Bohr warned about the dangers of nuclear weapons. He believed scientific discoveries should be used for peaceful purposes. Even though he worked in science during difficult times, he remained committed to openness and international cooperation. His moral values influenced policies and discussions about nuclear science. The story of the Bohr model demonstrates how one scientific idea can transform the world. It highlights how imagination, boldness, and careful thinking can lead to new discoveries. Bohr was not afraid to break old rules and propose something entirely new. His model reshaped physics and opened a path for future discoveries. Even though science eventually moved beyond his exact model, his ideas remain essential and influential. Today, every student who begins studying atomic physics starts with the Bohr model. It provides the first clear picture of atomic structure and energy levels. It serves as the foundation for deeper learning about quantum theory, electron configuration, and the physical laws that govern the universe. The simplicity of the Bohr model makes it unforgettable, and its historical importance makes it one of the greatest achievements in physics. Bohr's work represents the moment when humanity began to understand the atom, not as a mysterious object, but as something with a clear structure and predictable behavior. It was the start of the modern scientific era, a turning point that gave rise to quantum mechanics, modern chemistry, and advanced technology. Niels Bohr may have lived from 1885 to 1962, but his legacy continues to shape the world today. When scientists look back at the early, they often describe that period as the beginning of a scientific revolution, one that completely changed how humanity understands the universe. One of the most groundbreaking ideas to come from this era was the concept of energy levels and quantum jumps, both introduced by Niels Bohr. These ideas may sound simple now because students learn them early in science classes, but in Bohr's time, they were astonishing. They broke the old rules of physics and replaced them with a new kind of logic, one based on quantum behavior. Bohr's invention of energy levels and quantum jumps didn't just explain how atoms work. It laid the foundation for quantum mechanics, modern chemistry, electronics, and even modern technology. To truly appreciate the importance of these concepts, we have to dive deep into what Bohr proposed, why he proposed it, and how it transformed science forever. Before Bohr introduced energy levels, scientists already had some understanding of the atom, but it was incomplete. The discovery of the electron by J. Thomson in 1897 and the discovery of the atomic nucleus by Ernest Rutherford in 1911 gave researchers a general picture of atomic structure. Rutherford showed that atoms are mostly empty space, with most of the mass concentrated in a tiny, positively charged nucleus. Electrons, which carry a negative charge, move around this nucleus. But this raised a major puzzle. Why don't electrons spiral into the nucleus? Classical physics predicted that any charged particle moving in a circle should constantly lose energy. If electrons were orbiting the nucleus like planets orbiting the Sun, they would radiate energy as they moved. Losing energy means slowing down. Slowing down means falling inward. If this were true, atoms should collapse in a tiny fraction of a second. But clearly they do not. Atoms are stable. They make up everything, from stars to human bodies to the air. So something was missing from classical physics. This is where Bohr stepped in with one of the boldest ideas in the history of science. Electrons do not orbit the nucleus freely in any path. Instead, they occupy specific, fixed energy levels. This means an electron in an atom cannot have just any amount of energy. It must have one of the allowed energies. Bohr called these allowed values stationary states. These states were stable, and electrons in these states did not radiate energy. This solved the stability problem instantly. If electrons were confined to certain energy levels, they would remain in their orbits without falling inward. This was a groundbreaking moment. It meant that energy inside an atom was quantized, which means it comes in specific amounts, never continuous. To understand this better, imagine a ladder. You can stand on one step, or the next step, or the one above, but you cannot stand halfway between two steps. Bohr said that electron energies work the same way. An electron can be at one energy level or another, but never in the in-between space. This idea explained a huge scientific puzzle that had confused physicists for decades: the spectral lines of elements. When scientists passed electricity through gases or heated them, the atoms emitted light. That light, when passed through a prism, separated into colors. Each element produced a unique pattern of colors, called a spectral line spectrum. These patterns were mathematically predictable, but not scientifically understood. No classical theory could explain why atoms produced sharp, distinct lines instead of a smooth rainbow of colors. Bohr's energy levels provided a perfect explanation. He said that an electron emits light only when it moves from a higher energy level to a lower one. The color of that light depends on the difference between the two energy levels. Since the levels are fixed, the energy differences are also fixed, and therefore the colors are fixed. This idea matched the actual spectral lines perfectly, but Bohr went a step further and introduced another revolutionary concept: quantum jumps. A quantum jump is when an electron suddenly jumps from one energy level to another. In classical physics, particles move smoothly from one position to another. But in Bohr's model, electrons do not move smoothly. They teleport, in a sense, from one level to another without passing through the space between. These jumps are instantaneous and mysterious, something classical thinking could not accept. This idea shocked the scientific world because it meant nature behaves in ways that cannot be seen or imagined easily. For the first time, scientists realized that the microscopic world follows its own rules. Quantum jumps were not just a clever idea. They were necessary to explain real experiments. Whenever an electron absorbs energy, such as from heat or electricity, it jumps to a higher level, but it cannot stay excited forever. Eventually, it jumps back down, releasing a photon of light. this photon has an energy equal to the difference between the two levels. That energy corresponds to a specific wavelength, which produces a specific color. Bohr proved that every color observed in hydrogen's spectrum matched exactly with his energy level calculations. This was huge. For the first time, science had a model that described how atoms produce light, and it worked perfectly. Bohr's model showed that atoms were not random or mysterious, but behaved in predictable, quantized steps. The idea that electrons could jump between levels without physically moving through space was extremely strange. Even Einstein found it difficult to accept. Einstein believed the universe should follow smooth, continuous laws. Bohr said the opposite. At the atomic level, nature behaves in sudden jumps. This led to many discussions, arguments, and debates. Bohr insisted that the quantum world demanded a new way of thinking, one that classical logic simply could not describe. Bohr's energy levels also explained why atoms react differently in chemical reactions. Chemical behavior depends on how electrons are arranged around the nucleus. The outermost electrons determine how an atom bonds with others. Bohr's model allowed scientists to understand why some elements react strongly while others remain inert. This was a major breakthrough for chemistry because it connected atomic structure with chemical behavior for the first time. Even though Bohr's model was simple compared to modern theories, it was accurate enough to describe hydrogen, the simplest atom. It could also give approximate results for helium and other elements. But as atoms became more complex, Bohr's model ran into difficulties. He tried to refine it by adding elliptical orbits, introducing additional quantum numbers, and creating a shell structure. These improvements helped, but were not enough to describe all atomic behaviors perfectly. Eventually, new theories, such as wave mechanics by Schrödinger and matrix mechanics by Heisenberg, built on Bohr's ideas and created the full quantum mechanical picture we use today. Still, the importance of Bohr's concepts cannot be overstated. Without his introduction of energy levels and quantum jumps, scientists may have taken much longer to develop quantum mechanics. His ideas were the stepping stones for future discoveries. Energy levels also paved the way for modern technology. For example, lasers work because electrons jump between specific energy levels. LEDs use controlled quantum jumps to produce light efficiently. Atomic clocks, the most accurate clocks in the world, measure time using electron transitions. Computer chips and semiconductors depend on understanding how electrons occupy energy levels in materials. Bohr could never have predicted all these inventions, but his work made them possible. Perhaps the most remarkable part of Bohr's introduction of quantum jumps is how philosophical it was. Bohr realized that nature itself is not always smooth or continuous. Instead, it sometimes works in sudden, unpredictable steps. This idea challenged scientists to rethink everything they knew about physics. Bohr said that the microscopic world could not be understood using common sense alone. It required new concepts, new language, and a new way of thinking. This led Bohr to create the principle of complementarity, which said that quantum objects have dual behaviors, sometimes acting like particles, sometimes like waves, depending on how they are observed. This idea grew directly from his work on energy levels and quantum jumps. It helped shape the philosophical foundation of quantum mechanics. Bohr's introduction of energy levels and quantum jumps also changed how scientists viewed reality. It showed that the universe is not just made of matter, but also of quantized energy. Light, atoms, particles all are guided by the rules of quantum physics. This shift in thinking was one of the greatest intellectual transformations in history. Without it, modern physics, chemistry, and technology would not exist. By proposing that electrons jump between discrete energy levels, Bohr gave the world a new scientific language. Terms like ground state, excited state, energy level, and quantum leap became standard concepts. Today, these ideas are used not only in physics, but also in everyday language. We talk about quantum leaps to mean major progress, even though the original idea came from Bohr. Bohr's ideas were revolutionary because they embraced the strange and mysterious aspects of the microscopic world instead of trying to force them into classical thinking. He accepted that electrons might behave in ways that seem impossible. Instead of resisting this strangeness, he made it the foundation of his theory. This courage to think differently is what makes Bohr one of the greatest scientists of all time. Bohr's introduction of quantum jumps and energy levels did far more than explain atomic stability or the spectrum of hydrogen. It opened the doorway to a completely new way of understanding nature. Before his work, the microscopic world was a mystery. Scientists could observe strange patterns in experiments, but they didn't have a model that tied everything together. Bohr's theory provided that missing structure. It allowed scientists to see the atom not as a chaotic cloud of particles, but as an organized system that followed clear, quantized rules. These rules opened the path for future theories, technologies, and discoveries. To understand the true depth of Bohr's contribution, it is important to see how his ideas forced scientists to confront questions they had never asked before. For example, if electrons jump instantaneously between levels, what exactly happens in between? If an electron emits a photon when it falls to a lower level, how does it decide when to jump? Does the jump happen randomly, or does something trigger it? Bohr himself did not have complete answers to these questions, but he realized something crucial. Nature does not always reveal its inner workings in a continuous, smooth way. Some processes happen suddenly, some processes are inherently unpredictable, and some parts of nature cannot be explained using classical logic. One of the biggest challenges Bohr faced after publishing his atomic model was convincing others that quantum jumps were real and not just mathematical tricks. Many scientists found the idea unsettling. Even Einstein struggled with it. Einstein famously believed that God does not play dice, meaning he rejected the idea of randomness in nature. Bohr believed the opposite. He thought randomness was built into the foundations of the quantum world. This disagreement between two of the greatest scientists in history created some of the most famous debates ever recorded. These debates played an essential role in shaping the direction of quantum physics. Einstein would point out situations where he believed Bohr's ideas could not possibly be correct. Bohr would respond by demonstrating why quantum thinking was necessary. These discussions pushed both scientists to refine their ideas deeper than ever. Although they disagreed, they respected each other and helped shape the core principles of modern quantum mechanics. Their debates revolved heavily around energy levels, quantum jumps, and the strange behaviors that arise when particles transition between states. Bohr's work also inspired other scientists to expand quantum theory using new mathematical frameworks. For example, in 1925, Werner Heisenberg developed matrix mechanics, a powerful and abstract mathematical system that described how energy levels worked in atoms. Heisenberg's equations showed that the energy levels Bohr proposed were not just an idea. They were mathematically consistent with the behavior of electrons. Around the same time, Erwin Schrödinger developed wave mechanics, which described electrons not as particles moving in fixed orbits, but as waves that spread out around the nucleus. These waves had specific shapes for each energy level, known today as orbitals. These new theories did not replace Bohr's ideas, they refined and expanded them. Bohr's energy levels remained at the core of the new theories. Quantum jumps were still essential for describing how atoms emit or absorb light. Even the wave model showed that electrons could only exist in certain allowed wave patterns, which corresponded exactly to Bohr's original energy levels. This showed that Bohr's concept of quantized energies was correct, even if the picture of electrons orbiting the nucleus had to be updated. Bohr himself welcomed these developments. He understood that science evolves and that his models would eventually be replaced or improved. But he also recognized that the core idea of quantization, discrete energy levels, was here to stay. As more experiments confirmed the existence of these energy levels, scientists began applying the concept to other fields. For example, they discovered that atoms do not behave alone. They interact with each other through their electrons. These interactions depend heavily on energy levels, especially the outer-level electrons. This turned Bohr's ideas into a central concept for understanding chemical bonding. The periodic table, which organizes elements by their chemical properties, became much clearer thanks to Bohr's concepts. Chemists had long noticed patterns in how elements reacted, but they did not know why the patterns existed. With Bohr's idea of shells and energy levels, scientists realized that elements behave similarly because they have similar arrangements of electrons in their outermost energy levels. For example, the noble gases, all stable and non-reactive, have full outer shells. Alkali metals, which react strongly, have only one electron in their outermost level. These patterns could now be explained using the structure Bohr introduced. The idea of quantized energy levels also became essential in solid-state physics, the study of materials. Scientists discovered that electrons inside solids also occupy energy bands, the solid-state version of energy levels. These bands determine whether a material is a metal, an insulator, or a semiconductor. Semiconductor physics is the foundation of modern electronics, including computers, smartphones, solar panels, and LED. Every piece of digital technology depends on the behavior of electrons in energy bands. Without Bohr's concept of discrete energies, semiconductor theory would not exist. In physics labs today, many experiments continue to confirm Bohr's ideas. For example, when scientists trap single atoms and measure how their electrons jump between states, they observe exactly the behaviors predicted by Bohr. These experiments show that quantum jumps are real, momentary transitions that occur when electrons absorb or release energy. Some modern experiments even allow scientists to watch a single quantum jump happen in real time. This would have amazed Bohr, who proposed the idea long before such precise tools existed. Quantum jumps also play a central role in spectroscopy, the study of how atoms interact with light. Scientists use spectroscopy to analyze stars, diagnose diseases, measure gases in the atmosphere, and understand chemical compositions. When astronomers study distant stars, they rely on spectral lines to determine what elements those stars contain. Each element has its own unique pattern of light produced by its energy levels. Because Bohr explained how these patterns arise, spectroscopy became one of the most important tools in modern science. Bohr's ideas even helped in the early development of nuclear physics. Although energy levels in the nucleus are different from electron energy levels, the concept is similar. Particles in the nucleus also occupy discrete states. Nuclear transitions also involve quantized jumps, and these transitions produce gamma rays. This showed that quantized energy is not just an electron phenomenon, but a universal feature of microscopic particles. Bohr's early work paved the way for understanding the structure of the nucleus, nuclear reactions, and even nuclear energy. As quantum mechanics developed, Bohr applied his ideas to philosophy. He introduced the principle of complementarity, which stated that quantum systems can have multiple, seemingly contradictory descriptions that are both valid depending on the context. For example, light could behave like a wave or a particle, depending on how it was measured. Electrons could appear localized or spread out as waves. Bohr connected this to energy levels by showing that the act of measuring an electron's energy forces it into one of the allowed states. Bohr believed that complementarity was not just a scientific principle, but also a philosophical one. It showed that human observation plays a role in determining what properties are displayed by a quantum system. This did not mean that observers control nature, but rather that different experiments reveal different truths. This perspective became one of the foundational ideas of modern quantum theory. Bohr's introduction of quantum jumps also influenced language. The phrase quantum leap originally described an electron jumping from one energy level to another. Today, people use the phrase to describe a big improvement or breakthrough in any field. Even though the scientific meaning of a quantum jump is extremely small, the expression has become a symbol of progress and sudden change. This shows how deeply Bohr's ideas have influenced culture, not just science. Another important point is how Bohr's ideas affected education. In modern science classrooms around the world, students begin learning about atoms through simplified versions of Bohr's model. They learn that electrons occupy shells, that they jump between levels, and that these jumps produce light. Even though the modern quantum mechanical model is more accurate, Bohr's ideas remain the gateway to understanding quantum physics. Every textbook and every introductory course begins with energy levels because they provide a clear picture that helps students grasp the basics before moving into more complex concepts. Bohr was also a strong advocate for open scientific communication. He believed that discoveries, especially those involving quantum behavior, should be shared internationally. During times of global conflict, he encouraged scientists to work together and use their knowledge responsibly. His belief in cooperation helped shape scientific culture and encouraged the global exchange of ideas that has become standard today. In the final years of his life, Bohr looked back on his early work with a sense of humility. He acknowledged that his first model of the atom was not perfect, but he was proud of the foundation it created. He often emphasized that scientific progress happens in steps, some small, some large, and some revolutionary. His introduction of energy levels and quantum jumps was one of those revolutionary moments. It marked the point where science left the classical world and entered the quantum era. Today, Bohr is remembered not only as the father of quantum theory, but also as a guiding thinker who shaped the way science approaches the unknown. Energy levels and quantum jumps remain core ideas in physics, chemistry, technology, and philosophy. They form the basis of modern scientific understanding, whether through lasers, electronics, spectroscopy, or quantum computing. Bohr's ideas continue to influence how we explore the universe. His work showed that the smallest particles behave according to laws that challenge our intuition, but reveal the true nature of reality. When we look closely at the universe, closer than the eye can see, atoms behave in ways that are incredibly precise and surprisingly beautiful. One of the most striking examples of this precision is something called spectral lines. These are very thin, bright or dark lines of color that appear when the light from an element is split into its component wavelengths. Every element, hydrogen, helium, sodium, oxygen, and so on, has its own unique pattern of spectral lines, almost like a fingerprint. Scientists had observed these lines for many years, but no one could truly explain why atoms produced these exact patterns. That mystery remained unsolved until Niels Bohr introduced a revolutionary idea that changed the entire understanding of atomic physics. Before Bohr, scientists knew atoms had electrons and a nucleus, but the exact arrangement and behavior of electrons were unclear. Some early models like J. Thomson's plum pudding model and Ernest Rutherford's nuclear model attempted to describe the structure of atoms. Rutherford had shown that atoms have a tiny, dense nucleus with electrons orbiting around it. But this created a huge problem. If electrons were simply orbiting like planets around the sun, they should constantly lose energy and spiral into the nucleus. That would make atoms unstable, which we know is not true. Atoms are stable, long-lasting building blocks of matter. At the same time, scientists had studied the spectral lines of hydrogen and noticed a mathematical pattern in the wavelengths of the emitted light. The Balmer series, for example, showed that hydrogen emitted specific colors, not random ones, when energized. But there was no explanation for why atoms released energy in these exact amounts and no others. Something in the structure of the atom itself was controlling the color of light it produced. Bohr solved this mystery by introducing the idea of quantized energy levels for electrons. In simple terms, he proposed that electrons do not orbit the nucleus at just any distance. Instead, they are allowed only certain specific orbits, each one corresponding to a fixed amount of energy. An electron in a particular orbit has a specific, unchangeable energy value. This was a dramatic shift from classical physics, where energy could vary continuously. Here's the key concept. Electrons can jump from one energy level to another, but only by absorbing or releasing a precise amount of energy. This energy is given in the form of light, or more accurately, photons. A photon is a small packet of light energy, and its color depends on how much energy it carries. When an electron absorbs energy, for example, from heat or electricity, it can jump from a lower energy level to a higher one. This is called excitation, but electrons don't like to stay in higher energy states for long. Eventually, the electron will fall back to a lower energy level. When it does, it releases the exact amount of energy difference between the two levels in the form of a photon. This is the heart of why atoms emit specific spectral lines. Because energy levels are fixed and quantized, the energy released during these jumps also comes in fixed amounts. Each photon has an energy that corresponds to a specific wavelength of light. That wavelength turns into a specific color when we look at it through a spectroscope. Since each element has its own unique arrangement of energy levels, each element produces its own pattern of spectral lines. For hydrogen, Bohr was able to calculate the exact wavelengths of the spectral lines that had already been observed experimentally. This was a breakthrough. It proved that his model wasn't just a clever guess. It accurately described the reality of how atoms behave. This connection between theory and observation was so strong that it convinced many scientists of the power of quantum ideas. Bohr's explanation not only clarified why spectral lines exist, but also revealed that atoms were far more structured and predictable than anyone had imagined. Electrons were not randomly placed, nor did they move freely. Instead, They followed strict rules dictated by quantum mechanics. This understanding allowed scientists to map out the internal architecture of atoms, predict chemical behavior, and explore the nature of energy itself. Spectral lines became a tool for identifying elements even from far distances. For example, scientists can determine what stars are made of simply by analyzing the light they emit. Since each element has its own spectral fingerprint, the lines in starlight reveal the composition of the star. This is possible only because Bohr explained the mechanism behind these patterns. Furthermore, Bohr's model laid the foundation for future quantum theories. While more advanced quantum mechanics later refined the details, introducing concepts like orbitals, wave functions, and probability clouds, the basic idea of quantized energy levels remains central to modern science. It is used in lasers, LEDs, and even atomic clocks. Every time you see the colorful glow of a neon sign, the bright lines in a flame test during chemistry class, or the detailed images from astrophysical instruments, you are witnessing the direct consequence of Bohr's ideas. In summary, Bohr explained why atoms emit specific spectral lines by showing that electrons occupy fixed energy levels, and that the light we see results from electrons jumping between these levels. The precise energy difference between levels determines the color of the emitted light. Because each element has its own set of energy levels, it also has its own unique set of spectral lines. This explanation solved a long-standing scientific mystery and opened the door to quantum mechanics, transforming our understanding of the microscopic world. It remains one of the most important breakthroughs in physics, demonstrating the deep connection between energy, matter, and the nature of light. When we talk about the birth of quantum mechanics, we imagine a group of brilliant scientists trying to understand a universe that behaves in strange and unexpected ways. Among these scientists, Niels Bohr stands as one of the most important figures. His ideas, discoveries, and teaching influenced almost every key development in early quantum theory. In many ways, he didn't just contribute to quantum mechanics, he helped build its foundation. To understand why, it's important to know the scientific world before quantum mechanics existed. At the end of the 19th century, classical physics, the physics of Newton, Maxwell, and other great thinkers, was believed to explain almost everything. It described how planets moved, how objects fell, and how electricity and magnetism behaved. But when scientists began studying atoms and extremely small particles, classical physics fell apart. It simply could not explain the unusual behavior happening on microscopic scales. One of the biggest problems was understanding how atoms worked. Experiments showed atoms gave off very specific colors of light, proving they had exact energy values rather than a continuous range. But classical physics had no explanation for this. Scientists knew something was missing, and that something would eventually become quantum mechanics. Into this puzzle stepped Niels Bohr. The first major contribution Bohr made was his model of the atom, introduced in 1913. It was not perfect. Later scientists would refine it, but it was revolutionary because it introduced a new way of thinking about energy. Bohr said electrons could only occupy certain fixed orbits or energy levels. This idea directly contradicted classical physics, which assumed energy could vary smoothly and continuously. Bohr boldly declared that energy was quantized. It came in fixed, exact packages. This concept didn't just help explain atoms. It carried a deeper message. Nature itself behaves in discrete jumps, not smooth flows, at the smallest scales. This was a huge step forward and became one of the basic principles of quantum mechanics. Bohr's ideas also provided a bridge between Max Planck's early quantum ideas and the later developments from scientists like Heisenberg, Schrödinger, and Dirac. In fact, many of these scientists trained with Bohr, discussed ideas with him, or were influenced by his thinking. Without Bohr's leadership and guidance, their work might not have developed as quickly or as clearly as it did. One of Bohr's greatest contributions to the foundations of quantum mechanics was his introduction of the principle of complementarity. This principle states that particles like electrons can show different types of behavior depending on how they are observed. Sometimes they act like particles, other times they act like waves. Both behaviors are real, but they cannot be seen at the same time. They complement each other, giving a complete description only when considered together. Complementarity became one of the defining ideas of quantum mechanics. It explained the results of many confusing experiments and helped physicists accept that the quantum world cannot be understood through classical thinking. Bohr's principle taught scientists that the world at small scales follows its own rules, rules that may seem strange but are still consistent and measurable. Another major contribution was Bohr's role in shaping the Copenhagen interpretation of quantum mechanics. This interpretation became the most widely accepted way of understanding quantum behavior for many decades. According to the Copenhagen view, quantum particles do not have definite positions or velocities until they are measured. Instead, they exist in a cloud of possibilities described by a mathematical wave function. When someone measures the particle, the wave function collapses, producing one specific outcome. Bohr didn't develop all of the mathematics behind this idea, but he provided the philosophical structure and the physical interpretation. His explanations helped scientists make sense of the new equations that Schrödinger and Heisenberg developed. Bohr turned quantum mechanics from a set of strange formulas into a deeper understanding of nature. Bohr was also famous for his scientific debates with Albert Einstein. Einstein respected Bohr, but never fully accepted the randomness built into quantum mechanics. Einstein believed nature must be predictable and orderly. Bohr, however, argued that uncertainty and probability were essential parts of the quantum world. Their debates pushed quantum theory forward because both scientists sharpened their arguments, corrected each other's assumptions, and inspired new experiments. Without these debates, and Bohr's strong defense of quantum ideas, quantum mechanics might not have gained its solid foundation. Their discussions made the theory stronger, clearer, and more logically consistent. Bohr also played a major role as a teacher, organizer, and scientific leader. His institute in Copenhagen became the center of quantum research in the early 20th century. Young physicists from around the world traveled to work with him. Many of the greatest quantum physicists, like Heisenberg, Pauli, Kramers, and others, spent time learning from Bohr. His style of open discussion, deep questioning, and collaborative thinking created an environment where breakthroughs could happen rapidly. Bohr helped guide entire generations of scientists, and his influence can be seen in every major development in quantum mechanics. Even today, modern quantum theories like quantum field theory and particle physics rest on the foundational ideas he helped establish. Bohr's work also had a long, lasting impact on technology. The understanding of electron energy levels led to the development of lasers, semiconductors, LEDs, MRI scanners, quantum computers, and other advanced technologies. While these inventions came long after Bohr's time, they are built on the basic principles he helped introduce. In a very real sense, Bohr's ideas helped shape the modern technological world. In summary, Niels Bohr helped create the foundation of quantum mechanics by introducing quantized energy levels, developing the Bohr model of the atom, proposing the principle of complementarity, shaping the Copenhagen interpretation, leading scientific debates that strengthened the theory, and educating many of the physicists who built quantum mechanics into a complete system. His influence was not just through equations, but through ideas, teaching, and leadership. Bohr helped the world understand that the universe behaves differently at the smallest scales, and that new rules govern the quantum world. His contributions form some of the most important building blocks of the science that explains atoms, energy, and the structure of everything around us. One of the most fascinating chapters in the history of science is the series of debates between Niels Bohr and Albert Einstein. These debates weren't arguments over simple facts, they were philosophical battles over the very nature of reality. At the heart of their discussions was quantum mechanics, the theory that describes the microscopic world of atoms and particles. Bohr and Einstein were both brilliant, but they had very different visions of how the universe works. The debates between them are some of the most famous and influential in the history of physics, shaping how we understand the quantum world even today. In the early 20th century, physicists had discovered that the classical laws of physics, like Newton's laws of motion, could not explain what happened at the atomic level. Experiments showed that electrons, photons, and other tiny particles behaved in ways that seemed strange and unpredictable. Light, for instance, sometimes behaved like a particle, sometimes like a wave. Electrons in atoms jumped between energy levels without moving smoothly. These phenomena could not be explained by classical ideas of continuous motion and determinism. Scientists were puzzled, and the rules of nature at the quantum scale seemed almost magical. Niels Bohr was one of the first physicists to propose that the microscopic world operates according to different rules than the macroscopic world we experience. He introduced the idea of quantized energy levels, quantum jumps, and the principle of complementarity, the idea that a particle can display different behaviors depending on how it is observed. According to Bohr, the universe at the smallest scales is fundamentally probabilistic. Events do not always have a predetermined outcome. Instead, only probabilities can be calculated. This was a revolutionary and counterintuitive idea, even for physicists. Albert Einstein, on the other hand, believed in a universe governed by strict laws, where outcomes are predictable if all information is known. He had helped develop the theory of relativity, which explained motion, time, and gravity in precise terms. But Einstein was deeply uncomfortable with the uncertainty in quantum mechanics. He did not like the idea that nature could be fundamentally random. He famously said, "God does not play dice with the universe." This statement reflected his belief that there must be hidden rules or variables that could explain quantum phenomena deterministically, even if scientists hadn't discovered them yet. The debates between Bohr and Einstein were both scientific and philosophical. They met at conferences, especially the Solvay conferences in the 1920s and 1930s, where the most brilliant minds in physics gathered to discuss cutting-edge ideas. Einstein would present thought experiments designed to challenge quantum theory, and Bohr would respond with logical arguments defending it. One famous example involved the uncertainty principle, formulated by Werner Heisenberg. The principle states that certain properties of a particle, such as its position and momentum, cannot be measured exactly at the same time. Einstein tried to show that, in theory, it would be possible to measure both precisely, which would challenge the probabilistic nature of quantum mechanics. Bohr carefully analyzed the problem and showed why the principle still held true, defending the quantum framework. These debates were not just technical arguments, they touched on the nature of reality itself. Einstein wanted to know what was real in the quantum world. He asked questions like, do electrons have definite positions and velocities even when we don't measure them? Or do these properties only exist when we observe them? Bohr's answer was radical. In the quantum world, properties like position and momentum do not have definite values until they are measured. This was the essence of complementarity. Nature behaves differently depending on the experimental setup, and trying to describe it with classical certainty is impossible. In other words, reality at the quantum level does not exist in the same way we experience the macroscopic world. The Bohr-Einstein debates were famous for their intensity, yet they were conducted with respect and mutual admiration. Both men recognized the genius of the other. Bohr once said that Einstein's challenges forced him to think more deeply and rigorously about quantum mechanics. Einstein, in turn, appreciated Bohr's courage to embrace ideas that defied common sense. Their debates were more than arguments. They were a dialogue that advanced the understanding of physics and shaped the development of modern quantum theory. The influence of these debates goes far beyond historical curiosity. They clarified fundamental aspects of quantum mechanics that remain essential today. For example, Bohr's insistence that quantum mechanics is inherently probabilistic is central to everything from quantum computing to particle physics. The debates also highlighted the limits of measurement and observation, teaching scientists that the act of observing a quantum system can change the system itself. This concept is at the core of technologies like lasers, semiconductors, and atomic clocks. Einstein's challenges also inspired deeper research into the foundations of quantum mechanics. Although he was never convinced that quantum theory was complete, his questions led to experiments and discoveries that tested the limits of quantum mechanics. For instance, modern experiments in quantum entanglement and non-locality are direct extensions of questions raised during the Bohr-Einstein debates. In this way, their discussions continue to influence science nearly a century later. The debates also shaped the philosophy of science. Bohr's position suggested that human knowledge has limits, that we cannot always describe nature exactly as it is, only as it interacts with us. Einstein's position reminded scientists to question theories critically and search for deeper explanations. Together, they helped define the intellectual boundaries of quantum mechanics and inspired future generations to explore both its mathematics and its meaning. Beyond their technical contributions, the Bohr-Einstein debates represent a model of scientific dialogue. They show that disagreement is not a barrier to progress, but a catalyst. By questioning each other rigorously, both scientists sharpened their understanding and inspired others to think more deeply. Their debates demonstrate how science advances not only through experiments, but also through careful reasoning, skepticism, and collaboration. In summary, Niels Bohr and Albert Einstein worked together in some of the most famous debates in the history of science. These debates were about more than just equations, they were about the nature of reality itself. Bohr argued that the quantum world is fundamentally probabilistic, with particles existing in superpositions and only taking definite properties upon measurement. Einstein argued for a deterministic universe governed by hidden variables. Their discussions clarified essential principles of quantum mechanics, influenced countless experiments, and shaped the philosophy of modern physics. Even today, scientists look back on the Bohr-Einstein debates as a profound exploration of the limits of knowledge, the meaning of observation, and the strange but fascinating behavior of the quantum world. Niels Bohr is widely remembered for his groundbreaking work in quantum mechanics, but his influence extended far beyond atoms and electrons. He also made major contributions to nuclear physics and played a vital role in shaping scientific ethics, especially at a time when physics was becoming deeply intertwined with world-changing technologies, including nuclear energy and weapons. Understanding Bohr's role in both these areas helps us see him not only as a brilliant physicist, but also as a responsible, thoughtful leader who cared about the consequences of scientific discoveries. Bohr's contributions to nuclear physics after developing the Bohr model of the atom and helping establish the foundations of quantum mechanics. Bohr turned his attention to the nucleus of the atom. While the nucleus is extremely small compared to the whole atom, it contains almost all of the atom's mass and is central to nuclear physics. During the 1920s and 1930s, scientists were just beginning to understand the behavior of protons and neutrons inside the nucleus, and Bohr played a key role in advancing this knowledge. One of Bohr's most important contributions was the liquid drop model of the nucleus. Along with John Archibald Wheeler and others, Bohr proposed that the nucleus behaves somewhat like a drop of liquid. It can vibrate, oscillate, and even split under certain conditions. This model helped scientists understand nuclear reactions, including nuclear fission, the process in which a nucleus splits into two smaller nuclei and releases an enormous amount of energy. The liquid drop model became a foundational idea in nuclear physics because it provided a conceptual framework for understanding nuclear stability and reactions. It showed that the nucleus was not just a static mass of particles, but a dynamic system that could be studied, predicted, and manipulated. Bohr also worked on understanding nuclear reactions more generally. His theories helped explain why certain isotopes are stable while others are radioactive. Radioactivity, the process by which unstable nuclei emit energy and particles, had been discovered decades earlier, but the mechanisms were still mysterious. Bohr's insights clarified how the nucleus could release energy in predictable ways, laying the groundwork for future applications in energy production, medicine, and scientific research. Bohr's role in nuclear fission and its implications. Bohr's work directly influenced the understanding of nuclear fission. In 1938, Otto Hahn and Fritz Strassmann discovered that uranium nuclei could be split into smaller nuclei when bombarded with neutrons, releasing vast amounts of energy. Bohr recognized the significance of this discovery almost immediately. He traveled to the United States in 1943 during World War II to work with other scientists on nuclear research. His knowledge and leadership helped shape the early development of nuclear science. However, Bohr was acutely aware of the ethical implications of these discoveries. The enormous energy released in nuclear reactions made it clear that nuclear physics could lead to powerful weapons. Bohr recognized that the same principles that allowed humanity to understand the atom could also create weapons capable of destroying entire cities. He felt a moral responsibility to guide scientists and governments in using this knowledge carefully. Bohr's guidance on scientific ethics. Bohr was one of the earliest scientists to advocate for responsible use of scientific knowledge. He believed that breakthroughs in physics should not be divorced from their ethical and social consequences. During the Manhattan Project, the U.S. effort to develop nuclear weapons, Bohr attempted to communicate the dangers and responsibilities associated with nuclear fission. He urged governments and scientists to consider international cooperation and transparency, hoping to prevent a future in which nuclear weapons could dominate global politics unchecked. Bohr emphasized openness in science. He believed that sharing knowledge internationally would reduce the risk of secrecy leading to misuse. In 1945, he famously wrote to the United Nations, advocating for open discussion about nuclear energy and weapons. His vision was that science should benefit humanity, not endanger it. Bohr's efforts influenced later discussions on arms control and nuclear policy, highlighting the importance of scientists considering not just the can we do it question, but also the should we do it question. Ethics and leadership in science. Bohr's commitment to ethics was not abstract, it was practical. He mentored younger scientists and encouraged them to think about the societal impact of their work. At his institute in Copenhagen, he fostered a culture of debate, critical thinking, and responsibility. He insisted that scientific progress must go hand in hand with moral reflection. Bohr's guidance shaped a generation of physicists who were deeply aware of the ethical dimensions of their discoveries, from quantum mechanics to nuclear energy. Bohr also engaged in public discourse. He gave lectures, wrote essays, and spoke to policymakers about the responsibilities of science. He believed that scientists had a duty to communicate the risks and benefits of their work to society. This approach was unusual at the time, because many scientists focused only on the technical aspects of their research. Bohr demonstrated that being a great scientist also meant being a responsible citizen of the world. Balancing scientific innovation with responsibility, Bohr's dual focus on nuclear physics and ethics illustrates the balance he struck between innovation and responsibility. He understood that scientific discoveries could change the world in profound ways, both positive and negative. By contributing to the understanding of the nucleus, he helped create the foundation for nuclear energy, nuclear medicine, and advanced physics. At the same time, he worked tirelessly to ensure that these powerful discoveries were approached with caution and thoughtfulness. Bohr's philosophy reminds us that science does not exist in a vacuum. Every discovery carries consequences, and those who advance knowledge also carry responsibility. His ethical guidance set a standard for scientists everywhere, that brilliance must be paired with wisdom, and that understanding the universe comes with a duty to protect and improve human life. Legacy in nuclear physics and ethics today. Bohr's contributions to nuclear physics are still felt. The liquid drop model and his understanding of nuclear behavior remain fundamental in textbooks, research, and applications ranging from nuclear reactors to particle accelerators. His ethical principles continue to influence how scientists and policymakers think about nuclear technology, research ethics, and global security. The idea that scientists must consider the societal consequences of their work is now an integral part of modern scientific culture, thanks in large part to Bohr's leadership and foresight. In summary, Niels Bohr's impact went far beyond atoms and electrons. He made pioneering contributions to nuclear physics, helping scientists understand the behavior, stability, and reactions of the atomic nucleus. At the same time, he guided the ethical practice of science, emphasizing responsibility, transparency, and consideration of the consequences of powerful discoveries. Bohr's dual legacy, as a brilliant physicist and a moral compass for science, remains one of the most inspiring examples of how scientific knowledge and ethical responsibility can go hand in hand. Niels Bohr's contributions to science go far beyond the work he personally did in his laboratory. His discoveries, ideas, and leadership created a legacy that reshaped modern science and technology in profound and lasting ways. From the microscopic world of atoms to the technological innovations that power our daily lives, Bohr's influence can be seen everywhere. To understand the scope of his impact, it's important to explore how his theories transformed physics, chemistry, technology, and even the culture of scientific research itself. Bohr's foundational contributions to science. Bohr's scientific legacy begins with his revolutionary ideas about the atom. Before Bohr, the atom was largely a mystery. Scientists knew electrons existed and that atoms had a nucleus, but the behavior of these particles was not well understood. Bohr introduced the concept of quantized energy levels, showing that electrons could occupy only certain allowed orbits around the nucleus, and that they could move between these orbits by absorbing or emitting precise amounts of energy. This simple yet radical idea explained phenomena that had puzzled scientists for decades, such as the spectral lines of hydrogen. By providing a framework for understanding atomic behavior, Bohr laid the foundation of quantum mechanics. Quantum mechanics, the branch of physics that describes the behavior of matter and energy at microscopic scales, is now one of the cornerstones of modern science. Every particle, from electrons to photons, is understood in terms of quantum behavior. Without Bohr's pioneering work, this entire field might have developed more slowly or in a very different way. Influence on chemistry and materials science. Bohr's ideas did not just revolutionize physics, they also reshaped chemistry. Chemical reactions occur because electrons are transferred, shared, or rearranged between atoms. Bohr's energy level model made it possible to explain why certain atoms are reactive, why others are stable, and why elements show patterns in the periodic table. The modern understanding of chemical bonding, molecular structures, and electron configurations is rooted in Bohr's concepts. His work allowed chemists to predict reactions, design new molecules, and even develop complex pharmaceuticals with a precise understanding of molecular interactions. Materials science, which studies the properties and applications of materials, also benefited from Bohr's insights. Semiconductors, which form the basis of computers, smartphones, and modern electronics, depend on the quantum behavior of electrons in solids. Understanding energy bands and electron transitions, concepts that evolved from Bohr's model, made the design of transistors, LEDs, and solar cells possible. Every piece of modern technology that relies on the control of electrons is, in a way, a product of Bohr's foundational ideas. Technological innovations inspired by Bohr's legacy extends deeply into modern technology. For example, lasers, which are used in everything from barcode scanners to surgery, rely on electrons jumping between energy levels to produce coherent light. Similarly, atomic clocks, the most precise timekeeping devices in the world, function because of predictable quantum transitions in atoms. Quantum mechanics, which Bohr helped shape, also underpins magnetic resonance imaging MRI machines, a crucial medical technology, and guides the development of emerging quantum computing technologies that promise to revolutionize computing power and data processing. Even nuclear energy, both in power generation and scientific research, owes a debt to Bohr's ideas. His work on nuclear structure, energy levels, and reactions made it possible to understand and control nuclear processes safely. This knowledge has enabled not just electricity production, but also medical imaging, cancer treatment, and advanced materials research. Bohr, as a scientific leader and mentor, Bohr's legacy is not limited to his scientific discoveries. He was also a mentor and leader, shaping generations of scientists who would carry his ideas forward. At his institute in Copenhagen, Bohr created a hub for the exchange of ideas. He encouraged young physicists like Werner Heisenberg, Wolfgang Pauli, and George de Hevesy to explore bold new concepts in quantum theory. His guidance fostered creativity, critical thinking, and rigorous debate. Many of these scientists went on to make groundbreaking discoveries themselves, spreading Bohr's influence throughout the world. Bohr's leadership also helped establish a culture of international collaboration in science. He believed that scientific progress should transcend national borders, and that sharing knowledge openly was essential for the betterment of humanity. This approach influenced the development of research institutions, international conferences, and collaborative projects that remain essential in modern scientific practice. Philosophical and ethical influence. Bohr's legacy is also philosophical. Through his principle of complementarity and his debates with Einstein, he reshaped how scientists think about reality and observation. Complementarity, which explains that particles can exhibit multiple properties depending on how they are measured, challenged classical assumptions about determinism and certainty. This philosophical insight has influenced not only physics, but also the broader approach to scientific inquiry, emphasizing the importance of context, measurement, and the limits of knowledge. Bohr also stressed the ethical responsibility of scientists. He was deeply concerned about the social impact of discoveries, particularly nuclear technology. He advocated for openness, transparency, and international cooperation to ensure that scientific advancements were used responsibly. His guidance helped shape discussions around the ethical use of nuclear energy and advanced scientific research, highlighting that science carries both power and responsibility. Global impact and enduring influence. Bohr's contributions continue to resonate today. Quantum mechanics, built on his foundational ideas, drives modern electronics, communication technology, medical devices, and computing. His work in nuclear physics informs energy policy, medical treatment, and fundamental research in particle physics. Bohr's ethical philosophy guides how scientists consider the consequences of their discoveries, encouraging reflection on both technological and societal impacts. The reach of Bohr's legacy can be seen in classrooms, laboratories, and industries around the world. Students learn about quantized energy levels, atomic models, and quantum behavior, forming the basis for careers in physics, chemistry, and engineering. Researchers in quantum computing, nanotechnology, and materials science build directly on principles Bohr helped establish. Engineers designing new electronics or medical devices rely on a detailed understanding of atomic behavior, which originates in Bohr's pioneering theories. In conclusion, Niels Bohr's legacy reshaped modern science and technology in multiple ways. By developing the Bohr model of the atom and introducing the concepts of quantized energy levels and quantum jumps, he laid the foundation of quantum mechanics, which now governs our understanding of the microscopic world. His ideas transformed chemistry, materials science, and nuclear physics, making modern technology, from lasers and semiconductors to medical imaging, possible. Beyond his discoveries, Bohr's mentorship, leadership, and ethical guidance influenced generations of scientists and established principles for responsible scientific practice. Bohr's legacy is both scientific and humanistic. It demonstrates that revolutionary discoveries can drive innovation while emphasizing the moral responsibility that comes with scientific knowledge. Modern science and technology, in almost every aspect of our lives, continue to bear the imprint of his vision. From the smallest quantum particles to the most advanced technological devices, the world today is profoundly shaped by Niels Bohr's enduring contributions.